NanoHub U, online instruction.
Welcome to Lecture 3. So in the last lecture, we saw how transmission was related to the mean free path for backscattering. And I sort of stated that it is possible to theoretically evaluate these mean free paths for backscattering in terms of the microscopic physics, but we might also want to measure the mean free path for backscattering. That's the subject of this lecture. How do we determine the mean free path? And we will show that it is very simply related to the diffusion coefficient. So if we know the diffusion coefficient, we can extract the mean free path for backscattering. So we have been talking about this Landauer approach that we want to develop into a general transmission theory for the MOSFET. And we saw in the last lecture how we can relate transmission to mean free path for backscattering. And this is the expression that we will use when we derive the transmission theory of the MOSFET beginning in the next lecture. Okay, but the question for this lecture is, how can we measure this mean free path for backscattering? So we know what we're dealing with. So we know if the channel length is long or short compared to the mean free path. Well, I'll point out that it is easy to measure the mobility. Easy in quotes. You have to always do this carefully and experimentally to make sure you're actually measuring the thing that you're measuring. But measuring mobility is something that semiconductor engineers have done for a long time. So we know how to measure the mobility. So that can be done. You can find data that will report mobilities for different types of carriers in different types of MOSFETs. Now, we also know that the mobility and the diffusion coefficient are related by this Einstein relation near equilibrium. So we have D over mu is equal to KT over Q. Near equilibrium, the temperature is the lattice temperature, say 300 K. We may have measured data for the mobility, so we can use this relation to deduce the numerical value of the diffusion coefficient. Now, as we will show next, there is a very simple relation between the diffusion coefficient and the mean free path for backscattering. And we can use that simple relation then to extract the mean free path for backscattering from the diffusion coefficient. So we need to go back to our problem and look at it a little bit more. This is the model problem that we've been looking at. We have a flux of electrons injected from the left. Some emerges from the right. We have an absorbing boundary at the right so that nothing is re-injected. That absorbing boundary might simply be a high field region. We saw that high field regions act as good absorbing boundaries. Now, in this lecture, I'm not going to resolve these fluxes into independent energy channels the way that we did in the last lecture. I'm going to assume that they're averaged over all of the energy channels that are occupied with electrons. So we're just going to think of some average flux that's injected and some that's emitted. And what that means is that I'm going to attach a subscript to my transmission here. It's not a transmission at a particular energy. By T sub 0, I mean it's the average transmission for all of the energy channels that are occupied under these particular conditions. So the mean free path then is not going to be the mean free path at a particular energy. It's going to be some average mean free path over the channels that are occupied. Okay, so let's take another look inside this slab. We saw how we can resolve the fluxes inside the slab in the previous lecture. What I want to do now is to ask, what is the electron density at the left side and what is the electron density at the right side? Well, flux is just particle density times velocity. And I'm writing, even though this is an I here, I mean flux, so there's no charge here. Not a current, it's a flux of particles. Well, the electron density at x equals 0 consists of electrons with positive velocities that were injected from the positive flux. So it's just the positive flux divided by the average velocity in the x direction. So here are my double brackets here. So the first brackets mean I'm averaging over the angles. So if these are electrons moving in the xy plane, we've averaged over angles so that this is the average velocity in the x direction. And then I'm also averaging over the energy channels. That's the second set of brackets there. So we have a simple relation between the electron density due to positive velocity electrons. We have a similar relation due to the electron density with negative velocity electrons, assuming they're moving at the same velocity. And if I want the total electron density at x equals 0, I'll simply add these two together. So I have a flux that was injected. I have a 1 minus transmission that was backscattered. I add the two together. I get a 2 minus transmission times the injected flux. And then I divide by the average velocity in the x direction. Okay, now this average velocity in the x direction we've seen before. Under non-degenerate statistics, it's just the unidirectional thermal velocity, square root of 2 kT over pi times effective mass. So from here on out, I'm just going to use the unidirectional thermal velocity and assume that we're talking about non-degenerate conditions. All right, let's do the same thing at x equals L at the other end of the channel. So there I have a positive flux. So I have an electron density due to electrons with positive velocities. It's the positive flux divided by their velocity. But because of my absorbing boundary, at x equals L, I have no electrons at that point with negative velocities. So the total electron density is just given by the electron density due to electrons with positive velocities. So we have an expression for N of L. So I've got the electron density at the two ends of this slab. And the positive flux that emerges is just transmission times the positive flux that was injected. So I've got them all related to the injected flux at x equals 0. Okay. All right, so let's plot the electron density inside the slab. We know what it is at x equals 0. It's given by this expression. We know what it is at x equals L. It's given by this expression. Turns out you can show that the electron density within the slab varies linearly. And this comes from the fact that the flux within the slabs varies linearly, as we saw in the previous lecture. So we can draw a line between those 2 points, and now we have the electron density inside the slab. Okay, so let's see if we can relate this electron density to the flux. And then we'll see where we're going in this discussion. So let me subtract N of 0 minus N of L. So I'll simply subtract these two electron densities at the ends. So this is what we get. So we get a 2 minus tau minus another tau. So I get 2 times 1 minus transmission. Now the net current, I want to relate this to the net current through this slab. The net current is just transmission times what comes out, transmission times what was injected, because this is the current that emerges. And there's no negative current at x equals L. So this is my net current. So if I take my net current, I'll simply solve this expression for I of 0 plus, take transmission times that, and I have an expression for my net current in terms of the difference between these two carrier densities. Okay, now let me look at that. Let me lump these terms together out front. Let me lump the difference in carrier densities together. Let me divide by the length of the slab, and let me multiply by the length of the slab. And then let's look at what we have. We have a relation that relates the net current to the densities within the slab and some factors out front. The second factor there you can see is just minus the gradient of the electron density. Okay? Because things are linear there. The first set of quantities, if you look at the units, you can see that it has the units of diffusion coefficient. So I have net flux is diffusion coefficient times minus the gradient of the particle density, right? That's known as Fick's law. So we have seen that Fick's law applies in this nanostructure. Now this is quite interesting. We have an expression. We now know that the net current is minus diffusion coefficient times the gradient of the particle density. This is Fick's law. And this might not surprise you, but it should surprise you, because we have made no assumption about whether the slab is long compared to a mean free path or short compared to a mean free path or in between. Now, it is commonly thought, and often you'll see it stated in textbooks, that Fick's law only applies when the structure is many mean free paths long, when you're in the diffusive limit. We have derived something that looks like Fick's law, but it applies for nanostructures. It applies all the way to the ballistic limit, or as we approach the ballistic limit. Now, that might not be so surprising because when you look at this quantity, there is a slab length in it. So generally, we think of diffusion coefficient as a material property. It's not something that depends on the device or the device length. But we have a device length here. So we could say that, well, maybe we have derived a generalized fixed law, something with a device length dependent diffusion coefficient, and that's why it works. Okay, but something even more interesting happens. If we take this fixed law, if we take our expression for the diffusion coefficient, if we take our known relation between transmission and mean free path for backscattering and insert it in this expression, we get then an expression for this diffusion coefficient, and the channel length drops out. This is the expression that depends only on material properties. It's the same diffusion coefficient that you would get in a bulk material that is very, very long compared to a mean free path. So we have done two things. We have derived our relation between the diffusion coefficient and the mean free path. That's what we set out to do. We've also shown, rather surprisingly, that Fick's law of diffusion can be used at the nanoscale as well. Now, that's not something that we're going to do much with here. It's something interesting I wanted to point out. You can sometimes it's useful in analyzing nano devices to make use of Fick's law, which is a little bit counterintuitive, and generally it's something that people avoid doing. But it turns out that it can be done under certain conditions, specifically under the conditions we use to derive this relation. Okay, so this gives us now an expression that we can use to estimate the mean free path. Let's assume that we've measured the mobility, so we know the mobility. Let's assume that we're near equilibrium, so we can use the Einstein relation and find the diffusion coefficient. Now we have a numerical value for the diffusion coefficient. We now know how the diffusion coefficient is related to the mean free path for backscattering, so we can solve for the mean free path for backscattering in terms of our known diffusion coefficient. So a simple example to see how that works. Let's consider a silicon N-channel MOSFET at 300 Kelvin. The electron mobility might be about 250 centimeters squared per volt second. The appropriate effective mass to use for electrons in a two-dimensional inversion layer is the transverse effective mass, 0.19 times the electron rest mass. We can compute the unidirectional thermal velocity. It's 1.2 times 10 to the 7th centimeters per second. And now we can extract the mean free path for backscattering, assuming non-degenerate carrier statistics, by simply deducing the diffusion coefficient using the Einstein relation. The diffusion coefficient is 6.5 centimeters squared per second. And then we can solve for the mean free path. Turns out to be almost 11 nanometers. So current day technology has channel lengths of about 20 nanometers. The mean free path, reasonable estimate of a mean free path is something about 10 nanometers or so. So the current day devices we're going to expect operate in this quasi-ballistic regime where the channel is neither long nor short compared to a mean free path. Okay, let's do another example for a 3,5 field effect transistor at room temperature. 3,5 materials have very high electron mobilities. That's why the transistors are called HEMTs, high electron mobility transistors. The measured mobility in this case is over 12,000 centimeters squared per volt second. The effective mass is very light. The unidirectional thermal velocity is significantly higher than it was for silicon. We can go through the same analysis, compute the diffusion coefficient, use the diffusion coefficient to compute the mean free path. We find that the mean free path is quite long in 3,5 materials, specifically in indium-rich indium gallium arsenide. In this case, it's over 150 nanometers. So in this case, it would be significantly longer than high-performance transistor channel lengths, and we would expect to see 3,5 transistors operate quite close to the ballistic limit based on this simple calculation. So the key point of this lecture is that we can use the diffusion coefficient to estimate the mean free path for backscattering because the two are very simply related by this simple expression that we've developed here. We've assumed non-degenerate carrier statistics. It's straightforward, although a little bit tedious. To generalize this to Fermi-Dirac statistics, we'll just get some ratios of Fermi-Dirac integrals. I'll refer you to the lecture notes if you want to see how that's done. Okay, so with this, we have our understanding of transmission in hand, and we are now ready to develop the transmission theory of the MOSFET. We'll begin that in the next lecture. I'll see you there.